Welcome friends. So in the last lecture we have seen the graphical method of receiving and power circle diagram drawing. Now in this lecture we shall briefly demonstrate a numerical problem on this topic to illustrate the theories behind that. So we have a problem statement like that. We have a three-phase transmission line. We have a three-phase transmission line where we have A is equal to 0.951 degree and B is equal to 141 at an angle of 82 degree ohm. A synchronous phase modifier is connected at the receiving end so that receiving end voltage is kept 275 kilovolt at all the loads. I repeat, a synchronous phase modifier is connected at the receiving end. What is the purpose of synchronous modifier? So that to bring the receiving end voltage at 275 kV irrespective of the loads. Also, sending end voltage is kept at 275 kV. Now you need to compute two things. First of all, this output of this phase modifier when the no load is connected. Secondly, we have a load of 200 MVA at 0.85 power factor. So let us solve this problem. We require some data. We shall first compute what is the radius of the circle. We have radius the circle. What is the formula? Vs VR by B. So what is Vs? It is 275 kV. What is VR? It is 275 kV by what is B? It is 141.0, which is coming to be 536.35 MVA. This is the radius of the circle. Next we have center. Next we have the center of the circle. So x coordinate. What is the formula? Minus A by B VR square cos beta minus alpha. So what is A? It is 0.95 by B, which is 141.0 into VR square, which is 275 square cos beta. Beta is equal to 82 degree minus alpha is equal to 1 degree. So this should be coming to be minus 79.71 megawatt. Now be very careful while selecting the units because x coordinate is the real coordinate. That is why the unit y coordinate also. We have y coordinates also. Formula is minus A by B VR square sine beta minus alpha, which is equal to minus 0.95 divided by 141.0 75 whole square sine 81 degree. So why 81? Because of this. So it will be coming out as 503 minus 503.26. Now this time the unit should be megavar because it is y coordinate. Now after computing these three, we assume take 1 unit of graph paper, that will be equal to 100 megawatt along x-axis. Also 1 unit is equal to 100 megawatt along y-axis. So roughly, you see, roughly this 5. So roughly 536.35. This roughly 536.35 will represent roughly 5.5 units. Also, roughly this minus 79.71 will represent roughly 0.8 units. And roughly this 503.26, it represents roughly 5 units. Also, we have power factor for the second problem. Power factor is equal to 0.85 lagging. So cos phi r is equal to 0.85. So from there, phi r should be equal to 31.8 degree. So now we should draw the circle diagram. This should be y, this should be x. Now, if this represents roughly unit, so this is roughly 1, 2, 3, 4, 5. So roughly center is located something around here. Center is located, you see, it is x coordinate, that means 0.8 unit, and y coordinate is 5 unit. So center of the circle is roughly located around here, and this is the phasor that represents, this is the phasor that represents A by B VR square. A by B VR square, and which is equal to, in this case, it is actually A by B VR square. Now we have center, we have radius is equal to 5.5 units. So with having this center, a circle like this, we can draw a circle like this, having the radius roughly around 5.5 units. It is a rough sketch, right? It is a rough sketch. Now, coming to problem, first part of this problem, output of the phase modifier at no load. At no load. At no load means this point. At no load means this point. Let us say this point is P. So OP of phase modifier. It measures 0.27 unit roughly. 0.7 units roughly, which is equal to 270, sorry, not 270, 27 megawatt. 27 megawatt, it should be in lagging. That is the reactive power, reactive Q. On the second part, Second part, we should draw a load line. We should draw a load line by making an angle of 31.9 degree. So this angle is pi r, that is equal to 31.9 degree. This may be the position. Of course, I do not have the scale, but as I know the answer, so you know, this 200 MVA represents thing around here. 100 MVS represents something around here. So my corresponding intersection at this point, let me say this is Q dash. So when you measure this Q and Q dash, it will measure 35 centimeter or units rather. So which is equal to 135 megabar. Now this time it should be leading because this much is needed. This much is leading. So this is a small or brief description of a numerical problem. So with this, we shall end this lecture here. So more or less, the performance of the transmission line, more or less all the topics has been covered. So from the next lecture, we shall start our new module. Thank you.